Welcome back to the deep dive. Today, we're plunging headfirst into something pretty central to modern AI, transformers.
Absolutely. They're everywhere, aren't they?
Yeah,
Powering things like GPT-4, vision systems in cars, even search engines.
they really have transformed AI, literally. But here's the thing that gets me, and I think a lot of researchers, they're incredibly powerful, yes, but they often feel like these complete black boxes.
You put data in, you get amazing results out. But figuring out the how or the why behind it, that's tough.
It really is. So imagine if we could, simplify these things, actually justify them mathematically, maybe even make them fully interpretable.
That's the million-dollar question in AI right now, isn't it? We're great at building things that work. The what, but the why they work. Or how exactly. That's often missing.
Yeah, and that lack of transparency, it's not just academic, it's a real hurdle for using AI in critical areas like, say, medicine or finance. You need trust.
You need accountability. You need to know why it made a decision.
Exactly. Which brings us neatly to today's topic. We're looking at this really groundbreaking new paper. Just got accepted to ICML 2025, so it's right at the cutting edge.
Oh, ICML acceptance, that's significant.
It is. And it proposes this radically simplified transformer architecture. They call it attention only.
Attention only, so stripping out some core components.
Pretty much. But it's not just about making the models smaller, although that's a huge practical win, obviously.
Right. Efficiency matters.
It's more fundamental. They're reframing how we think about transformers, seeing the core mechanism, attention, through this lens of being a denoising operation.
Okay, denoising. That's an interesting perspective. Cleaning up the signal, essentially.
That seems to be the core idea. So our mission today is to unpack this. Look at how this minimalist design isn't just some clever hack.
It's got mathematical backing, you're saying.
Apparently so. Deep mathematical justification. And incredibly, it seems to achieve performance pretty close to standard, much bigger transformers.
Comparable performance with a simpler model. That is interesting. And potentially sheds light on what's actually happening inside.
Helping demystify that black box. Exactly. So let's set the scene a bit more. Standard transformers, like we said, huge success.
Undeniable. Bert, GPT models. They've pushed the field forward dramatically.
They are typically deep, dozens, maybe hundreds of layers,
Right.
and just crammed with parameters. Millions. Billions.
Billions, easily, in the larger models. They're massively over-parameterized.
And that scale, that complexity, that's what makes them these opaque black boxes, right?
Precisely. The depth and the sheer number of parameters, while they give the model capacity to learn complex patterns, they also make it incredibly difficult to track what's going on layer by layer.
You can't easily point to why it generated a certain word or classified an image a certain way.
It's like trying to understand, a city's traffic flow just by looking at cars entering and leaving without seeing the roads or traffic lights inside.
Good analogy. Now, researchers have obviously been trying to simplify things for a while, trying to figure out what the essential bits are.
Oh, absolutely. Lots of work on ablation studies, removing components, tweaking things. And the consensus seems to be that self-attention and those skip connections are really fundamental.
The bare bones, almost?
Kind of.
Yeah.
Skip connections, for example, are crucial. There's theory showing they help prevent things like rank collapse.
Rank collapse. Sounds bad. What is that, basically?
It's where, as information passes through layers, it sort of gets squashed, loses its distinctiveness,
Yeah.
like all the features blur together into one mush. Skip connections help maintain that clarity, preserving information from earlier layers.
Okay, makes sense. So theory pointed towards attention and skips being key.
Right. But a lot of that earlier theoretical work on, say, pure self-attention networks, it often didn't have strong empirical validation. They didn't always show how these stripped-down models actually performed on real tasks, like language or vision.
So the theory was there, but the practical proof, maybe less so.
Or at least the link between the theory and practical performance wasn't always fully drawn out.
Got it. And this new paper, this is where they make a leap. What's their core idea about how these representations are learned?
This is where it gets really interesting, I think. Their fundamental insight is about the goal of representation learning in these models.
Okay.
They propose it's not just about encoding the input. It's about compressing the initial token representations, which might be noisy, towards something specific.
Compressing them towards what?
Towards a mixture of low-dimensional subspaces.
Okay, mixture of low-dimensional subspaces. That definitely sounds like academic research talk. Can you break that down a bit?
Let's try. So imagine you break your input, like a sentence, into tokens, right? Words or parts of words.
Standard practice.
Each token starts as a vector, maybe high-dimensional, maybe a bit noisy, unclear. Now, think about existing ideas, like the linear representation hypothesis, basically. Okay. Tokens encode features linearly. And the superposition hypothesis, where a token might represent a mix of different features simultaneously.
Right, like a word can have multiple facets of meaning.
Exactly. This new model sort of formalizes that. It views these initial token vectors as being drawn from a mix of noisy, low-rank distributions. Think of each low-dimensional subspace as representing a distinct category or type of meaning, like maybe one subspace for animals, one for verbs, one for places.
So like conceptual buckets.
Sort of. And initially, a token might be a bit messy, trying to fit into several buckets at once, noisy. The transformer's job, in their view, is to clean that up, to figure out the main meaning bucket or subspace that token really belongs to, and push it cleanly into that subspace.
So it's like sorting and filtering the meaning, getting rid of the noise and clarifying which concept it represents.
Precisely. It's a process of denoising and categorization, pushing representations towards clearer, more distinct low-dimensional structures.
That's a very elegant way to think about it. So if that's the goal, compressing noisy tokens into these cleaner subspaces, how does the main workhorse multi-head self-attention MHSA fit in?
And this is the really transformative part of their argument. They reinterpret MHSA itself, not just as a way for tokens to attend to each other and weigh relationships.
Which is the standard view, right?
Instead, they propose MHSA acts primarily as a denoising operator.
A denoising operator. Okay, like noise reduction on an audio track or sharpening a photo.
Exactly like that. Think of your input data image pixels, text tokens, as initially being like a slightly blurry, noisy image. Each layer of attention in this attention-only model acts like a specialized filter.
A filter that does what?
It sharpens the image. It systematically removes the irrelevant noise, the fuzziness, and enhances the underlying signal, the core information.
Yeah.
It compresses those noisy initial representations into their proper supporting subspaces.
Back to those meaning buckets, cleaning them up and putting them in the right place.
Exactly. It's a conceptual shift. Attention isn't just about reloading things. It's fundamentally about cleaning up the representation of those things.
That really changes how you think about building the model, doesn't it? If attention is the denoising step.
It absolutely does.
Yeah.
And that leads to their architectural innovation, instead of just stacking layers based on intuition or trial and error.
Which is how many deep learning models are built, let's be honest.
Often, yes. They took a more principled approach. They designed the architecture by, and this is their term, unrolling iterative denoising operations into a deep network.
Unrolling iterations. So basically taking a mathematical denoising process and translating each step of that process into a layer of the network.
That's the idea. It's a way to construct the network based on the mathematical function it's supposed to perform. Very principled.
And the result is this attention-only transformer, or AO2.
Yes. And it's incredibly streamlined. It consists only of self-attention operators, layer after layer, with skip connections bridging them.
Only attention and skips. What about layer normalization? Or more significantly, what about the feed-forward or MLP layers? They're usually considered pretty crucial.
Layer normalization can be added optionally, they note, and it helps performance. But crucially, no MLP layers. They're completely absent in the core AOT design.
Wow. Okay, removing the MLP layers is a huge departure from standard transformers like GPT or BERT. They usually have big MLP blocks in every layer.
They do. Typically alternating attention and MLP. This model just uses attention.
So if you're building a model based on this denoising principle, you need theoretical guarantees, right? You need to prove it actually does denoise effectively. Does the paper offer that?
It does, and this is arguably the academic centerpiece. They introduce a way to measure the signal-to-noise ratio, the SNR, of the token representations as they pass through the model.
Okay, quantifying the clarity of the signal.
Exactly, and their key theoretical result, presented as Theorem 1, is quite powerful. It proves that each layer of their proposed attention-only transformer improves the SNR of the token representations at a linear rate.
A linear rate, meaning it gets consistently better with each layer, and predictably so, not like diminishing returns.
A linear improvement in SNR per layer, that's a strong guarantee. It provides a solid mathematical justification for why stacking these attention layers works for this task. It's not just empirical observation, it's a proven property of the architecture derived from the denoising perspective.
That's actually really significant. It moves from it seems to work to we can prove how it works at a fundamental level.
Precisely. It adds that layer of rigorous understanding that's often missing. And they don't just leave it a theory, they show experimental results, like figures in the paper, that visually support this denoising effect layer by layer.
Theory backed by empirical observation. Nice. Okay, so elegant theory, streamlined architecture, mathematical proof of denoising. But does it actually work on real problems? How did it perform in their experiments?
Right, the practical test. They ran extensive experiments, image classification on standard benchmarks, and also language tasks, causal language modeling, like predicting the next word, and also in-context learning.
A good range of tasks. Were they trying to beat the state of the art?
They state pretty clearly that wasn't the main goal. It was more about validating the theory and demonstrating the potential of this simplified architecture, proving the concept holds water.
Makes sense. So how did this lean, attention-only machine stack up against the standard, heavier models?
And here's where it gets really surprising. Despite being much simpler, lacking those MLP layers entirely, the AOT achieved performance that was comparable to standard architectures. They mentioned models like GPT-2, CRATE for Vision, VIT.
Comparable, seriously. Even without the MLPs.
Comparable. And here's the kicker.
There's more.
It achieved this comparable performance using nearly half the number of parameters compared to the standard models.
Whoa. Hold on. Half the parameters? For similar performance?
Roughly half, yes. That's a massive reduction in model size, memory footprint, computational cost. It's a huge win for efficiency.
That's incredible. It really makes you question the role of those MLP layers then, doesn't it? If you can get comparable results without them.
It absolutely forces that question. And the paper tackles it directly. By comparing their AOT with standard models, they could effectively ablate the MLPs, see what happens when they're removed, or, in their case, added back to the AOT.
And what happened when they added MLPs back to their attention-only model? Did performance shoot up?
This is another key insight. They found that adding MLP layers back into the AOT architecture did not improve zero-shot performance on the language tasks they tested.
No improvement on zero-shot tasks. So tasks the model hasn't specifically trained for, relying on its general knowledge, MLPs didn't help there.
According to their findings, no. Which strongly suggests that, at least in this denoising focus framework, the MLP layers might be, well, maybe redundant. Or perhaps their role is much more specific, maybe more about fine-tuning for particular downstream tasks rather than core representation learning or generalization.
That fundamentally challenges the standard wisdom about transformer design.
It certainly complicates the picture and suggests the interplay between attention and MLPs might be more nuanced than we thought. Maybe attention is doing more of the heavy lifting in representation learning than previously credited, especially when viewed as this denoising process.
And this simplicity, this focus on attention as the core operator, does it help with the black box problem? Is the AOT more interpretable?
That's another claimed benefit, and they provide evidence for it. Because the model is simpler and grounded in this denoising idea, it seems easier to understand what's happening.
How do they show that?
They include visualizations, like attention heat maps. And these maps apparently show that different attention heads within the AOT learn to focus on distinct semantic features in images.
So you can actually see what different parts of the model are paying attention to. Like one head looks at textures, another at object shapes.
Something along those lines, yes.
Mm-hmm.
It provides a much clearer window into the model's internal workings compared to trying to decipher a huge, complex standard transformer. It directly addresses that interpretability challenge.
Okay, that's compelling. Simpler, efficient, interpretable. What about more complex emergent behaviors, like in-context learning, where models learn on the fly from the prompt?
They tested that too. They showed that their AOT models could perform in-context learning, specifically for tasks like linear regression and sparse linear regression, just by seeing examples in the prompt.
Without specific fine-tuning for regression.
Exactly. And they achieved performance close to GPT-2 on these tasks, which is significant because it shows this simplified architecture retains some of those sophisticated learning capabilities we see in much larger models.
So it's not just a denoising machine, it can also learn new tasks contextually.
It seems so. The denoising framework doesn't preclude these more complex learning abilities.
Okay, let's step back and try to wrap this up. What's the big picture takeaway here for people listening, for the field of AI?
I think the biggest takeaway is that maybe, just maybe, we can build AI that is powerful, efficient, and understandable. It challenges the bigger is always better mentality.
Right. It suggests that focusing on core mathematical principles, like framing attention as denoising, can lead to simpler, more elegant solutions.
Exactly. It's a shift towards principle design rather than purely empirical scaling. If we understand the mathematical foundations better, we might be able to build models that are inherently more interpretable and efficient.
It gets rid of some of the mystery, perhaps.
It aims to, yes. Building AI we can not only use effectively, but also genuinely understand and trust.
So here's a final thought to leave everyone with. If attention, this core piece of modern AI, can be reframed and mathematically justified as a denoising process, leading to simpler, interpretable models.
What else?
What other complex components in our current deep learning toolbox might be hiding a simpler, more fundamental mathematical principle underneath?
Could we apply a similar lens to other neural networks? Could this be the start of a new wave of white box AI design, where interpretability isn't an afterthought, but built in from the start through mathematical understanding? It's definitely provocative. It encourages us to look beyond just scaling up existing architectures and to dig deeper into the mathematical underpinnings. What other fundamental operations are these networks really performing? Finding those answers could unlock the next generation of AI systems.
A really fascinating possibility. It suggests a future where AI is perhaps less alchemy and more principled engineering.
Hopefully.
Yeah.
More transparent, more efficient, more reliable. That's the goal.
Well, this has been a truly insightful deep dive. Thanks so much for breaking down this complex but potentially transformative research.
My pleasure. It's exciting stuff.
Absolutely. A big thank you for joining us on the deep dive. We hope this gives you a new perspective on where AI might be heading. Until next time, keep digging deeper.